Welcome to the 13th lecture in the series on the fundamentals of transport processes. I will just briefly go through where we are now and how we are going to proceed. So far, we have been discussing unidirectional transport of mass, heat and momentum. Unidirectional transport implies that there is transport only in one particular direction. It could be unsteady, it could be a function of time, but spatially there is transport only in one particular direction. Okay. So, for example, the transport between two flat plates. Okay. In the case of a heat transfer problem, there are two plates kept at two different temperatures, okay, T1 and T2, okay, and there is transport of heat between these two. The case of concentration, two plates at two different concentrations of solute C1 and C2, and then there is transport between these two due to the difference in concentration. The fluxes in the case of heat transfer are given by Fourier's law. In the case of mass transfer is given by Fick's law. Momentum transfer, two plates, one moving, the other stationary. In this case, the shear stress is related to the gradient in the velocity by Newton's law of viscosity. Okay. And of course, there could be sources or sinks of heat, mass and momentum within the domain. A source of heat, if there is a reaction exothermic or endothermic, if there is a physical transformation process which either takes in or gives out heat. In the case of mass, there could be a source due to reactions. If the constituent whose concentration is being described here is a product, then there is a source of mass. If it is a reactant, there is a sink of mass. We will see in the case of momentum transfer, a source refers to a body force, force acting per unit volume within the fluid. Okay. And in all these three cases, we get remarkably similar equations for heat, mass and momentum. Okay. So, for example, in the case of heat transfer, we get an equation of this form. The time variation of temperature is equal to the diffusivity times the second derivative with respect to the z coordinate. The z coordinate is the coordinate in which there is a variation of temperature plus any source of heat that is there. In the case of mass transfer, we get an equation that looks exactly the same, except that the concentration is substituted for the temperature and the mass diffusion coefficient is substituted for the thermal diffusion coefficient. In the case of momentum transport, the route that we followed to get the momentum transport equation was a little different from heat and mass transport. In the case of momentum transport, the fundamental equation that we used was that the rate of change of momentum is equal to the sum of the applied forces. Forces could be of two types. One is surface forces due to deformation and the other is body forces. Okay. However, despite the small difference in the way that we derived these equations, the final equation that you get looks remarkably the same. The final equation looks of this form: dux by dt is equal to nu times d square ux by dz square plus any body force divided by density. Note that we have written down the momentum conservation equation only for the x component of velocity. Therefore, in this case we are considering only the x component of the momentum. How do we treat momentum as a vector? That we will deal with later on. For now, we only deal with one particular component of the momentum. Flow is only in the x direction, and there is a variation of the velocity only in the z direction, and the momentum conservation equation is identical to the mass and heat conservation equations, except that the velocity ux is substituted for c and t. The kinematic viscosity nu or the momentum diffusivity is substituted for the mass and the thermal diffusivity, and then we have a source term which is basically the body force divided by the density. Okay. Now, we used this so far to solve two different types of problems. The first was an unsteady diffusion problem. When written for heat transfer, the situation was as follows. I have two plates. The temperature of both of these plates is equal to 0. Even if it is not 0, as I told you, I can always define a scale temperature, which is the temperature minus the temperature of the plates, which can be defined to be 0, okay, throughout the domain. At the initial time, at time t is equal to 0, I increase the temperature of the bottom plate instantaneously by heating it to another temperature, which is T star is equal to 1, the scale temperature is equal to 1. We discussed how one can define the scale temperature in such a way that it varies between 0 and 1. So, this was the situation. Temperature everywhere is 0. At time t is equal to 0, the temperature of the bottom plate is switched to 1, and then we want to see how the temperature evolves in time. The fundamental equation was the thermal diffusion equation, and in this equation we neglected the source and sink terms because there are no sources and sinks in this configuration. And secondly, we would expect that initially only the bottom surface is at temperature 1 at time t is equal to 0, everywhere else the temperature is equal to 0. As time progresses, the effect of heating from the bottom plate penetrates through the fluid until in the long time limit you recover the linear temperature profile between the two plates. The first problem we considered was one where this penetration depth for the temperature is small compared to the height h. So that the boundary condition T star is equal to 0 at z is equal to 1, okay, at z is equal to h, T star is equal to 0 can effectively be written as T star is equal to 0 as z goes to infinity, because the top surface is so far off that effectively the temperature distribution is not affected by the location of that top surface. So, if we set the boundary condition T star is equal to 0 as z goes to infinity, then we tried to obtain a scaled coordinate. If the penetration depth was comparable to the height h, we would simply have scaled the z coordinate by h itself. However, the penetration depth is small. So, h cannot be a factor in determining the temperature profile, and it cannot be used for scaling the z coordinate. So, we had 3 dimensional variables: time, z, and the momentum, the thermal diffusivity alpha. These were the only 3 that were left over, and they contain 2 dimensions, length and time. On that basis, you can define only one dimensionless group, and that group we had defined as z by root of alpha t. That is a similarity variable psi, and just dimensional analysis was telling us that the temperature should depend only upon this parameter. It should not depend independently on z, alpha and t, but it should depend on those only through this particular combination. That is what dimensional analysis told us. Okay. So, we had converted the equation from independent variables z and t to the independent similarity variable psi, and sure enough we ended up with an equation which was an equation only in terms of psi itself. Okay. The initial equation was second order in space, first order in time. So, you needed 2 boundary conditions, 1 initial condition. When we re-expressed it in terms of psi, we found that one of those boundary conditions at z going to infinity was identical to the initial condition at t is equal to 0. And on that basis, we were able to obtain a solution for the temperature field, okay, in terms of the variable psi alone. Okay. And this is a function that decreases as you go up. It's an error function, okay, and this provides you a universal temperature profile as a function of z by square root of alpha t, rather than in terms of z and t separately. Okay. So, this was a similarity reduction that we used, and this is valid when the penetration depth is small compared to the height h. Penetration depth we found out was square root of alpha t. Therefore, this is valid only at very early times when t is small compared to h square by alpha. Okay. Okay, so, in that case you can use the similarity solution. And the similarity solution basically reduces the partial differential equation to an ordinary differential equation on the basis of dimensional analysis. Okay. You can calculate the flux, and the flux decreases at t power minus half, okay, as time progresses. We looked at another example where we can use the similarity solution even though it is not a time dependent flow, even though it is a steady flow. That was the adsorption into a falling film. Okay. Even though this is a steady flow, when I write out the equation after I do the shell balance, the equation has exactly the same form. As you can see in the red here at the bottom left, the equation has exactly the same form as the unsteady balance equation. And so, I could just define a similarity variable where t was replaced by x by u, where u was the velocity itself. And from this we got the first of our Nusselt number correlations for the diffusion into a falling film. Okay. We calculated the flux, and from that we managed to get a correlation which was for the Nusselt number or the Sherwood number, okay, in terms of the Peclet number. Okay. So, this correlation was obtained on the basis of dimensional analysis. It is valid only in restricted cases. There were conditions on this. We made assumptions when we derived these equations. Okay. The first assumption was that the penetration depth is small compared to the height h, and that is when L by h, the length of the film divided by the thickness, is small compared to a Peclet number based upon h. Second assumption we made was that the velocity is nearly a constant, and that gave the same identical condition, that L by h has to be small compared to the Peclet number. And the third one was that we neglected diffusion in the streamwise direction, and that is when the Peclet number is large compared to 1 based upon the downstream distance x. So, that is a summary of how we derived a correlation for the average flux for mass transfer into a falling film of liquid. And this was once again based on similarity solution, but not on dimensional analysis. We just used the fact that the equations for the unsteady flow and for this situation are exactly the same, boundary conditions are the same, so the solution is the same. That works for any linear problem. If the problem is linear in the concentration field and you have well specified boundary conditions, there exists a solution, and that solution is unique. Now, what happens if the penetration depth is not small compared to the thickness? Okay. So, in that case, there is an additional scale in the problem, which is the height h. So, we can define a non-dimensional distance as z divided by h. Now, we get a scaled equation of the form d squared t star by d time square is equal to d squared t star by d z star square, where we have scaled time by the time required for the diffusion over a distance of the order of h. Okay, so, we scale time by the time required for diffusion over a distance of the order of h. Okay. And at steady state you get a linear profile 1 minus z, which is shown here. Okay, so, there is a steady linear profile. However, at initial times when you just switched on the temperature at the bottom, the temperature is different from the steady solution. So, we separated out the temperature into a steady plus a transient part. In the limit of time going to 0, you recover the steady solution, but at initial time when you just switched on the heating at the bottom, the temperature is different. The difference between the actual temperature at that time and the steady solution is the transient part of the temperature. Okay. And we wrote an equation for the transient part of the temperature. Okay. It looks identical to the equation for the total temperature. And we wrote the boundary conditions for the transient part of the temperature, and this is important. These are homogeneous boundary conditions. That means that transient part is 0 at both boundaries. However, at time t is equal to 0, the transient part is different from 0. At time t is equal to 0, the temperature is 0 everywhere. The steady temperature is still 1 minus z. So, the transient part, which is the difference between the temperature and the steady temperature, is non-zero. So, therefore, the flow is being forced by this non-zero value of the transient part of the temperature at time t is equal to 0. Okay. There is no forcing at the boundaries, because T star is equal to 0 at both boundaries. We went through the separation of variables procedure to calculate the time dependence. Okay. You write the function as a function of t times a function of z and insert this into the equation, divide throughout by z times t. You end up with an equation in which the left hand side is only a function of time, right hand side is only a function of distance z. Therefore, both of these have to be constants. Are they positive or negative constants? From the z equation, we saw that if it is a positive constant, we get a solution z is equal to 0, because you get exponentially increasing and decreasing functions, which cannot be 0 on both boundaries unless both constants are 0. If it is a negative constant, you get sine and cosines, and in this case we get a non-trivial solution. Okay. If my solution is of the form sin n pi z by z star, then this is 0 both at z is equal to 0 as well as z is equal to 1, provided n is an integer. So, the boundary conditions place a restriction on this constant beta. Okay. The boundary conditions place a restriction on the constant beta, not just on the constants you get from the solving the differential equations a and b. Okay. So, these are the eigenvalues for this problem. Okay. You put the constant into the equation for the part theta that depends upon time, and then solve it, and you get an exponential decrease in time. Okay. And you put these two together and you get a series solution with the coefficient a n, the eigenfunction or the basis function in the spatial coordinate sine of n pi z, and then there is a part that depends upon time, which basically tells you the decay rate of this component of the solution proportional to the basis function sine n pi z. Okay. And then we looked at how to obtain the coefficients a n using orthogonality conditions. Okay. So, if I write S n is equal to sine n pi z and I define the product, inner product S n times S m as integral 0 to 1 dz of S n of z times S m of z, this is 0 if n is not equal to m, it is equal to half when n is equal to m, and it is given by this symbol, this delta function symbol. Okay. So, basically the solution is being separated into a series of basis functions with each with a coefficient in front. Okay. And those coefficients are similar to, for example, the representation of a vector in 3-dimensional space. It is equal to the unit vector times a component. Okay. The unit vector is the basis vector, the component gives you the quantity, the coefficient in front. In a similar manner, the solution is being expressed as a component, this coefficient a n times the basis function S n, and that S n is being determined from orthogonality relations for the basis functions. Okay. And on that basis, we had actually found out what those coefficients were, okay, and from that we got the final solution for the concentration field. Okay. So, this ended up being the final solution for the temperature field. Similar solutions arise for the concentration and momentum fields. Okay. In the case of a concentration field, the entire system is at constant concentration initially, and at time t is equal to 0, you increase instantaneously the bottom surface concentration. Momentum field, everything is at rest initially, at time t is equal to 0, you start the motion of the bottom plate. Okay. So, that is separation of variables technique. The first one was a similarity solution. Now, we will look at one more way of solving these equations for the specific flow, which is oscillatory in time. Okay. Same configuration as before. Okay. Z is equal to 0, z equals h, my coordinate system x, z, okay, with a fluid in between. Okay. This top surface is stationary, ux is equal to 0, okay, whereas the bottom surface is oscillating, u times cos, where omega is the frequency of oscillations. Okay. And we would like to know what is the velocity field within the flow. Okay. So, the problem is for an oscillatory velocity field at some bottom at the bounding surface, what is the entire velocity field within the flow. Okay. So, that is the problem. These oscillatory flows have many applications. For example, the flow in the human body, blood in the human body is an oscillatory flow. Many machines have oscillatory motion like reciprocating machines and so on, and the forcing is oscillatory in time. It could be with a fixed frequency, it could be with a waveform that is not exactly sinusoidal, but so long as it is periodic in time, these oscillatory flows can be treated by the method that I am going to show you. Okay. So, the governing equations again, okay, dux by dt is equal to the kinematic viscosity times d square ux by dz square. Okay. So, that is the equation for the velocity field, which we had derived by taking a balance over a small shell within the fluid earlier. If we take a balance over a small shell and then use Newton's law for the shear stress, we get an equation of this form, where nu is the kinematic viscosity. How do we, what are the boundary conditions? Okay. At z is equal to h, the velocity ux is equal to 0, and at z is equal to 0, ux is equal to capital U times cos omega t. How do we scale the variables in this case? The scaling for z is natural, z star is equal to z by h. That is the scaling that we have used repeatedly throughout this section, because h is the distance of relevance here, the distance over which there is a variation in the velocity. How about velocity ux? The obvious way to scale it is by the amplitude of the oscillations, capital U, because that gives you the maximum velocity that is attained during the oscillations. Okay. So, it is natural to scale ux star is equal to ux by u. How about time? When we solved the unsteady flow problem, we scaled time by h square by nu, because there was no time scale in the problem itself. Therefore, we felt it natural to scale it by the time it takes for diffusion to take place across the channel of distance h. The time it takes is approximately h square by the diffusion coefficient. In this particular problem, we have a well defined frequency for oscillations, omega, a well defined time period for oscillations, that is 2 pi by omega. Okay. Since there is an intrinsic time scale in the problem, the time scale for the oscillation itself, it is natural to scale the times by the frequency of oscillations itself. That is to define t star is equal to omega times t. Okay. So, these are the three length, time and velocity scales in the present problem. This differs from what we have been doing earlier in the sense that there is an intrinsic time scale in the problem, that is the frequency or the time period of the oscillations. Okay. And therefore, it is natural to scale time by define the non-dimensional time as omega times t. put all of these together into the governing equation, okay, what I will get is u times omega dux star by dt star is equal to nu u by h square d square ux star by dz star square. Okay. Just putting in the time and distance and velocity scales. Okay. And of course, I can cancel out u on both sides, and finally, I will get omega h square by nu d ux star by dt star is equal to d square ux star by dz star square. So, that is my final dimensionless non-dimensional equation, which contains this non-dimensional parameter. Okay, it contains this non-dimensional parameter here. Okay. What is that parameter? It is equal to h times omega by the kinematic viscosity. Kinematic viscosity has dimensions of length square per unit time. Omega times h square also has dimensions of length square per unit time. So, this is basically a ratio of the time scale for diffusion and the time scale for oscillation. The time scale for oscillation is 2 pi by omega, the time scale for diffusion is h square by nu. The ratio of these two, the time scale for diffusion divided by the time scale for oscillation, is this non-dimensional number. I will refer to this in the present lecture as a Reynolds number based upon the frequency of oscillations omega. Okay, so, this is a Reynolds number based upon the oscillation frequency omega. In a sense, it gives you a ratio of inertial and viscous forces, because the right hand side of the equation contains the viscous stresses. The left hand side is the rate of change of momentum, an inertial term. So, this Re omega gives you the ratio of the inertial and the viscous forces. Okay. So, this is our conservation equation, Re omega times partial ux by partial t is equal to partial square ux by partial z square. And the boundary conditions on this, okay, at z star is equal to 1, top plate z is equal to h, and therefore, z star is equal to 1. Okay. You have ux star is equal to 0. Okay. Bottom surface z star is equal to 0. Ux was equal to u cos omega t. Okay. So, ux star is ux by u and t star is omega t. Therefore, I will get ux star is equal to cos t star. Okay. So, this is the partial differential equation that we are trying to solve for an oscillatory flow. Okay. Now, this has an initial condition that is oscillatory in time, okay, cos t. Okay. And cos function is generally inconvenient to handle. A simpler way of handling it is to actually define a complex velocity field. Okay. So, let me just say how it is defined and then justify it. Okay. So, I will define a complex velocity field ux plus such that the actual velocity field that I have in my problem, okay, ux star is equal to the real part of ux plus. Okay. So, I am defining a complex velocity field. The actual real velocity field that I am after is the real part of this complex velocity field. Okay. The differential equation for this complex velocity field Re omega dux plus by dt star is equal to d square ux plus by dz star square. identical to the differential equation for the actual velocity field. The boundary conditions at z star is equal to 1, u x plus is equal to 0, and at z star is equal to 0, u x plus is equal to e power I t star, where I is the square root of minus 1. Okay, so, u x plus at z is equal to 0 is equal to e power I t star. Okay. And you can easily see that if I take the real part of this entire equation, okay, R e omega is already real. So, if I take the real part of this entire equation, I do get back the equation for my actual velocity field. Okay, so, I do get back the equation for my actual velocity field when I take the real part of the equation for the complex velocity field. In addition, when I take the real part of the boundary conditions, note that z is still a real number. Okay, z is a coordinate, is still a real number. When I take the real part of the boundary conditions, I recover the boundary conditions for my actual velocity field. So, the only inhomogeneous term in the boundary condition is that z is equal to 0, u x plus is equal to e power I t star. And I take the real part of that, I recover cos of t star. Therefore, if I solve this equation with this boundary condition and then I take the real part of that, I will end up with the velocity u x. Okay, so, that is the basic idea. And it is more convenient for me to deal with exponentials than with sine and cosine functions. Okay, so, this is an easier way to get the solution than to actually do it for the real sine and cosine functions. So, how do we solve this equation? Okay, so, my equation is R e omega d u x plus by dt is equal to d square u x plus by dt in d. dz square. Okay. With boundary conditions at z star is equal to 1, u x plus is equal to 0, and at z star is equal to 0, u x plus is equal to e power I t star. Now, the differential equation, the partial differential equation is linear in u x plus, and it is driven by an oscillatory driving at the wall. Okay. Whenever you have a driving with which is oscillatory on a linear system, the response will also be oscillatory with the same frequency. Okay. Because the system is linear in the velocity, right, and the driving is oscillatory, therefore, you will end up with a solution that is also oscillatory with the same frequency. Okay. Therefore, I know that u x plus u x plus, which is a function of z and t, it has to be oscillatory in time with the same frequency as the driving. Okay. It has to be oscillatory in time with the same frequency as the driving, okay, times some function. Okay. It can be any function of z, but it has to be oscillatory in time with the same driving as the driving of the bottom plate in time. Okay. So, because it is a linear equation, it is being driven by an oscillatory velocity at the bottom surface, the final solution that I get should also be oscillatory in time. Okay. Now, this form of the solution, okay, I can now insert into the differential equation. Okay. Okay, so, I insert this form of the solution into the differential equation and you will get R e omega u x of z into the derivative of e power I t with respect to time, which is basically I times e power I t, okay, will be equal to, now the right hand side contains a derivative only with respect to z. Therefore, this will be equal to u x of z, I am sorry, d square u x by d z square d square u x tilde into e power I t. Okay. So, that is what I get when I substitute this form of the equation into the of the solution into the governing equation. And now, of course, I can cancel out e power I t on both sides. Okay, I can divide throughout by e power I t, okay, to get a final equation which is d square u x by d z square, okay, is equal to I r e omega times u x. Now, this equation is an equation only in the z coordinate. We had got rid of the time variable by postulating that the solution has to be of this form because it is being driven by an oscillatory flow in time. Okay. And once I put this form of the solution in, e power I t will cancel on both sides and I get only an ordinary differential equation in the z coordinate for this variable, this u tilde. For this u tilde, I get an ordinary differential equation, okay, in the z coordinate alone. What about boundary conditions? Okay. At z star is equal to 1, u x plus was equal to 0, which implies that u x tilde is also equal to 0. Okay. At z star is equal to 0, u x plus was equal to e power I t star. Okay. Since u x plus is equal to e power I t star, which is equal to e power I t star into e power I t star into u x tilde. Okay. Therefore, u x tilde will be equal to 1. Okay. So, now I do not have any time dependence in either the equation or the boundary condition, because I use the fact that if it is being driven by sinusoidal profile at velocity at the bottom, the velocity everywhere will be a sinusoidal velocity with the same frequency, because it is a linear governing equation. And of course, I can solve for this. I can solve this equation to find out what is u x tilde. From that, how do I get the solution? I go back and get u x plus is equal to u x tilde of z e power I t star, okay, and then u x star is equal to real part of u x plus. Okay, so, that finally gives me the solution for the flow within the domain. Okay. So, this equation is quite easy to solve. Okay, it is a second order differential equation. So, the solutions are sine and cosine functions or exponential solutions. Okay. The final solution for u x tilde will be of the form a 1 e power square root of I r e omega times z star plus a 2 e power minus square root of I r e. Okay. Square root of I is 1 by root 2 plus I by root 2. Okay. And then if I impose the boundary conditions, ux tilde is equal to 0 at z is equal to 1 and ux tilde is 1 at z is equal to 0, I will get the final solution for the velocity field as ux tilde is equal to e power root of I r e omega z star minus e power root of I r e omega into 2 minus z star divided by 1 minus e power 2 root of I r e omega. So, that is the final solution. You can verify that at z star is equal to 1, this will be identically equal to 0. At z star is equal to 0, this will be identically equal to 1. Therefore, it satisfies both of these boundary conditions. Okay. So, from this I will get ux plus, which is equal to into e power I t star, and then ux star will be equal to the real part of ux plus. So, that will be my final solution. Okay. Of course, I could evaluate this real part numerically and then find out the velocity profile at every point within the flow. Okay. However, in order to get a physical understanding, it makes sense to first look at limiting cases. Okay. The first limiting case is the limit r e omega small compared to 1. Okay. In this limit, you can actually take this velocity profile and do an expansion in the small parameter r e omega. Okay. Do an expansion in the small parameter r e omega. Okay. The leading order term will be identically 0 and then you will get a first correction, okay, and that first correction will be of the form ux tilde is equal to 1 minus z star. Okay. So, that will be the first correction that you get, okay, for when you do an expansion in square root of r e in the limit of r e omega small compared to 1. Okay. This implies that ux plus is equal to 1 minus z star e power I t star. Okay. And therefore, ux star is equal to 1 minus z star cos t star. Note that ux star is equal to 1 minus z star. This part alone is the solution for the steady velocity between two plates. Okay. If you have velocity is equal to 0 at z star is equal to 1 and 1 at z star is equal to 0, if it is just a steady flow, you would get a solution of the form 1 minus z star. In this case, I am getting a solution of the form 1 minus z star times cos t star. Cos t star is the instantaneous velocity of the bottom surface. Okay. So, the solution that I get is the same that I would get for a steady flow, except that the velocity of the surface is the velocity at that particular time. Okay. Why is that? Okay. What does r e omega physically mean? Okay. As I discussed before, r e omega is equal to omega h square by nu, okay, which is equal to h square by nu divided by 1 over omega. Okay. H square by nu is the time taken for diffusion over a length of order h. Okay, it's the time for diffusion over a distance comparable to h. 1 over omega is the period of oscillation of the bottom plate. So, when h square by nu is small compared to 1 over omega, the time taken for momentum diffusion is small compared to the period of oscillation. That means that the momentum diffuses almost instantaneously across the entire plate. Okay. So, instantaneously the momentum has equilibrated over the entire surface, over the entire fluid, and therefore, the velocity that you get is identical to the velocity you would have got for a steady flow, except that the velocity at the bottom surface is the instantaneous velocity at that instant in time. Okay. So, when momentum diffusion is fast, there is an equilibration of velocity across the channel, and the velocity response profile is a steady velocity profile which responds instantaneously to the instantaneous velocity of the bottom surface. Okay. So, in that case what I would get is something that looks like this. Okay. As the bottom surface velocity, if it is this way, you will get velocity that looks like this. As the velocity decreases, you get a linear profile. Halfway through the cycle you get this, then you get negative, larger, and then it comes back all the way. Okay. So, you get a linear profile at every instant in time, a linear profile with the instantaneous velocity at the bottom surface as the driving velocity for the steady flow. Okay. So, this is the case where RE omega is small compared to 1, when momentum diffusion is very rapid. Okay. And when the time required for momentum diffusion is small compared to the time period for oscillation, okay, of the bottom plate. What happens when RE omega is large compared to 1? Okay. In this limit, I can once again solve the velocity profile. Okay. If RE omega is large compared to 1, okay, then I will have only the exponentially decreasing part of the solution, because the coefficient of the exponentially increasing part will go to 0. Okay. Think of a solution at the bottom surface into an infinite fluid. There is an exponentially increasing and decreasing part, and if you are into an infinite fluid, you can have only the exponentially decreasing part. You can get it by an analysis of this equation, okay, taking the limit of RE omega large, okay, but a simpler way is to just use physical understanding, and on that basis you will get Ux tilde of Z star will be equal to e power minus root of I RE omega times Z star, okay, which means that Ux plus of Z star e power I t star, okay, and Ux star is the real part of this one, okay, the real part of this one. Okay. I will not go into the details, but basically you will get e power square root of by 2 into Z star into cos of So, you get a solution that looks something like this. First of all, this solution is not in phase with the driving at the bottom surface. Okay. In the previous case where the RE omega was small, the solution was exactly in phase, and the reason it was in phase was because diffusion is dominant, okay, and diffusion is, if you like it, a resistive element. Okay. It does not introduce a phase change, whereas this solution is not exactly in phase, and that is because inertia is important. Okay. So, it has a component proportional to cos and a component proportional to sine of omega t, okay, with the same frequency of course, but it does have a phase shift. Secondly, this decreases as square root of Re omega times Z star. It decreases exponentially when Re omega is large compared to 1. Okay, so, we are considering the limit where Re omega is large compared to 1. This solution decreases exponentially into the fluid. Okay. The exponential decreases goes as square root of Re omega times Z star, okay, which is equal to square root of omega h square by nu times Z by h, okay, which is Z by square root of nu by omega. Okay. So, in this case, the penetration depth for the exponential decrease is this one. Okay. In this case, the penetration depth for the exponential decrease is square root of nu by omega. Nu recall nu has dimensions of length square per unit time, omega has dimensions of time inverse, therefore, this will give you a length scale. Physically, what does it mean? Nu by omega power half is the distance over which diffusion can take place over a time period 1 over omega. Period of the oscillation is 1 over omega. Nu by omega power half is the distance over which the diffusion will take place over a time period, which is 1 over omega, where omega is the frequency of the oscillations. And the Reynolds number is large, that means that nu by omega is small compared to h. Okay. So, the Reynolds number is equal to omega h square by nu, this is equal to h by nu by omega per half the whole square. Okay. So, this number is large. What that means is that h is large compared to the distance over which momentum diffusion can take place over a time period 2 pi by omega, where omega is the frequency. So, we have a bottom plate that is oscillating with a period omega or a frequency 2 pi by omega. Within that period omega or within the time period 2 pi by omega, the momentum from the bottom plate due to its forward motion diffuses a certain distance. By the time it has diffused further, the plate has already reversed its direction and it has come the other way, and therefore, you get a momentum disturbance that is in the opposite direction, and those two will cancel out, resulting in penetration of the velocity profile only over a finite depth, not throughout the distance h. So, because of that, the momentum disturbance is confined to a thin region near the surface which is oscillating, because the frequency is large enough, the period is small enough that the period of oscillation is much smaller than the time taken for the momentum to diffuse across the entire channel. Okay. So, in that case, you will get a boundary layer at the bottom where the momentum diffusion is restricted, okay, and the thickness of that is nu by omega per half. Okay. Once again, h is no longer a relevant variable, because momentum does not diffuse that far when the frequency is large. It diffuses only a small distance from the bottom surface, and that distance over which it diffuses is nu by omega per half. So, taking the limits Re small compared to 1 and Re omega large compared to 1 gives you a better physical understanding of what is happening in the two limiting cases, and of course, you can always do the numerical solution of this quite easily in order to get numerical values of the solutions for the velocity profile everywhere in the channel. This is an approach that we will use regularly or repeatedly in this course. We will derive equations, do scalings, try to get limiting cases, and use those limiting cases to give us a better physical understanding of what is happening within the system. Okay. Similar problems can also be posed for concentration and for mass and heat transfer. Okay. They are a little more difficult to realize in practice. In heat transfer, you would have to heat the bottom plate with a sinusoidal temperature. It can be done if you have a heater with the correct frequencies. Mass transfer is much more difficult to realize. Okay. You cannot very easily have a sinusoidal. There are oscillatory reactions, but it is not very easy to realize in practice to have a sinusoidal variation in the concentration of the bottom surface. Okay. So, this is how we deal with oscillatory flows. And so far we have looked at 3 different ways: similarity solutions, separation of variables, and oscillatory flows, all for systems where there is no source or sink within the flow. Next lecture we will start looking at some systems which have sources and sinks within the flow, and how do we analyze it for these cases. So, we will close this discussion of oscillatory flows here and continue in the next lecture on unidirectional flows once again in the presence of sources and sinks of concentration, momentum, etc. So, we will see you in the next lecture.